during the original Ames studies that by an architect that you might want to start with smaller habitats and then build up, but I think O'Neill's vision was just too overwhelming, so they kept building the first habitats in these large sizes. So about 8 or 10 years ago, I had the idea, well, what's the minimum size habitat that you could build, and how would that help the economics to get this started? So the minimum would be something like not building Jamestown in the city, it would be building a homestead. And this shows a very humble homestead from the Library of Congress of the United States. And so we took a look at how habitat size, initial habitat size versus the economics works out. If you're going to build a small habitat and you're going to rotate it and maintain 1G, then you really get away from those large geometries, but you still need 1G. So what you're driven to is bolo, which is 2 spears on a string. And here you have a 2-kilometer tether that's spun at 1 RPM, producing about point gravity. And so this bolo habitat is the geometry that you're driven to the smaller sizes. And this just shows the amount of people in the large sizes. In O'Neill cylinders, it could be from 2 to 20 million people. And in the Stanford Torus, which was done in the studies at Ames here in 74, 75, it was about 10 to 40,000 people. And for the bolos that we looked at, it was in the hundreds. And if you go small, there's a few people, but that didn't turn out to be necessary. So the O'Neill Glaser model then is a parametric financial model, and it looks at the demand for space solar power, and what they looked at was just the new generation demand. In other words, they didn't replace all the old stuff, just all the new demand. And if some power plant went out of business because it was too old, then they would replace that. And then, of course, they look at the economic benefit that comes from the space solar power, and calculate net present value curves. So we set up the model, and then after we checked it, made sure it was giving us the numbers that we expected from the previous studies, we looked at different parameters. For instance, what if we were in the O'Neill habitats, the O'Neill Glaser model, it was 44% of the workers were actually working on the space solar power. And we tried upping that to 80%, and you get a little improvement in your break-even time and cost if you do that, but it's not really substantial. And then we looked at different geometries, and this shows the populations and different torus, sphere, cylinders, and bolos. And we looked at the low-density bolos, which had the same people for surface area as O'Neill. And then we looked at higher density bolos that would be more like a space station or a Starship Enterprise environment, apartment building. So this is the way those calculations come out. And you can see that building the O'Neill sphere, the cylinders and the spheres is costs quite a lot. And your break-even time is about 35 years. And that was about where it was during the Ames conference. If you go to other geometries, like for instance the large spheres, then you can get a smaller break-even time, but your costs get pretty high. But if you go to bolos, to the small bolos, then you get the best break-even times, and your maximum costs during your program are the lowest. And so that drives you to begin by economic reasons with bolo habitats. And this shows how the size of the habitat affects your economics. So for a 100 man year, and that's construction person years, which is about an 8,000 person bolo, then you see that your break-even is about year 25. And if you go to a 5 man year habitat, which is time back down to about year 23. So there is some benefit, but obviously anything in that range is still very favorable. And this just shows that if you take some point in your economic earnings in the future and look at your habitat size, and you're beginning with only 50 people, that you end up having a sweet spot somewhere around the 5 man-year habitats. So that's about 300 person habitats. And being able to start with 50 people in your program is very reasonable, because if you think about it, with 8 shuttle flights and 3 Soyuz flights, you end up putting about 50 people in space in 1 year. So if you left them there, that would be your whole workforce you would need to begin the program. So this is sort of a conclusion chart. It shows the O'Neill-Glaser model as calculated from the Ames, Curreri Ames conferences and presented in the science article and to the Science and Technology Committee of the United States Senate. And we're using now $1,875. And you can see the benefit that you would get if you use the 5 man-year habitats. And that's this curve. So you gain about 30% in break-even time, from about 35 years to about 27 years. And your maximum expenditure goes down to only about 20%. So by beginning with these small habitats, you have much more favorable economics than was presented originally by O'Neill. So this is something that people could look at and perhaps fund today. The other thing that was mentioned in the original Ames studies was that, and this was part of what the architect was talking about, was to say, hey, if we start with these small holes, we might be able to build those up later into the large vista habitats. And so we looked at that situation, and what we did was we maintained the small habitats for the first 10 years of the program. And then after that, we went to the large vista O'Neill habitats with 45,000 people. Turns out that once you get past that first 10 years, your amount of manufacturing capability in space is so high that the model becomes unsensitive to habitat size. So after that first 10 years, then you're able to build the large O'Neill large vista habitats. The other thing we did was we said, if you remember, after that 25 years, your profit starts to go way up, because the money it costs to build the satellites is much less than their cost. Profit margin is very high. So we said, well, what if at that point, rather than return profits to investors, we would reinvest the profits in not space solar power, but in real estate. In other words, fund more habitats as many as we can with that money, and fund the people's transportation into those habitats. And if you do that, so then you go from space energy to space real estate economy. If you do that, then whereas you would have about 40,000 people using the O'Neill-Glaser model in space in 25 years, if you were to invest your profits in real estate in space, you end up with about 1 million people in space in 25 years. And so the conclusion is that by using the O'Neill-Glaser concept, and even though there's been a lot done in space solar power since that time, the Glaser satellite was studied considerably and optimized for use of extraterrestrial materials. And so in that case, it was easy to use. But it's a worst case scenario, because a lot of the things since then, like for instance, the microwave emitters could be phased array, be much lighter. So this model is very pessimistic, very conservative to the real costs that you would have to. And so in conclusion then, by beginning the first 10 years with small habitats, about 350 people, that after 10 years you could build your O'Neill habitats with large vistas and beautiful living space, and with little financial problems, the same time, you would be supplying all of the new energy from that Earth needs for space without any greenhouse gases.
All right, and our last talk is membrane-based habitat wall architectures, revolving structures, and comprehensive resource recycling in Homestead stage space colony development by Sherwin, Gormly, and Flynn. Sherwin Gormly is of Dynamac Corporation here at Ames, and Flynn is here at Ames. Thank you very much.
So Sherwin couldn't be here on Flynn, and I'd like to start off by saying that usually when I give this presentation, I'm a little bit concerned that it's too far out there, too much in the future, and after seeing some of the presentations at this conference, I realized that it's probably a little bit too conservative, so I'd like to apologize for presenting something that could conceivably occur in our lifetime. So the motivation for this work is the realization that I've been working for NASA for about 20 years, and I think there's been 3 major human space exploration projects that have been proposed during that period of time, and all of them have been shot down. All of them shot down because of cost, basically. It turns out, if you go before Congress and you ask for $400 billion, they say no. They say it over and over again. It's kind of like going on a date, you know. By the 3rd date, nothing's happening. It's probably time to realize that nothing's ever going to happen. So this work that we're doing there is really focused on basic tenet that we need to take all the knowledge that we've learned over the last 20 years in Eclipse design and just throw it away and start over again. Cutting the cost of the Eclipse system in half just isn't good enough. We need an order of magnitude reduction in the cost of the Eclipse system, or else we're just not going to go anywhere. It's not going to be feasible. So that's where the water wall concept comes from. The water wall concept comes from the idea of, so if you look at Eclipse and you think, what would be the most dramatic thing we could do to reduce the cost of the Eclipse system? Well, the first thing that comes to mind is, well, let's just not have an Eclipse system. Let's just get rid of it entirely and have no Eclipse system. Let's just make it an architectural question. Let's just fire all the Eclipse engineers and hire a bunch of architects and let the architects design a system that will keep human beings alive in space for a certain mission duration. And that's what the membrane water wall concept is. It proposes a system that basically leverages off the fact that you have to have radiation protection. If you're going to go to Mars, if you're going to go out to the branch point, you're going to need to have radiation protection. And that means you're either going to have some sort of a polymer barrier or you're going to have a water wall. Well, if you're going to have a water wall, maybe that's your ecosystem. Maybe just the fact that you have a water wall gives you the ability to provide all the functions that you need to keep human beings alive in space. And we'll just let the radiation people keep on down their books as far as all the mass associated with it. And we're just going to get a free ride along with it. And that's basically the approach that we're talking about. And this can be used for inflatable structures and for rigid habitats as well. Of course, it's better suited for an inflatable type structure, but it doesn't mean that it's exclusive to that. So the concept basically is you're going to have a spacecraft. The spacecraft's going to have some sort of a structure associated with it. It's probably going to have a water wall associated with it. Can we integrate with that? And can we produce a life support system based on that water wall idea? So this approach would allow water recycling, air treatment, and solids residual treatment integrated into a water wall for radiation protection. It would also provide an ability to evolve that, let's say, an inflatable structure with a water wall into a rigid structure as a function of time. So early in the mission, you have a water wall, and you're using that system to recycle all your waste. You're building up solids inside that water wall, and eventually you're displacing the water that's in that wall with solids that have been derived from the human waste, eventually resulting in a rigid structure that could provide some capability for future missions out in the past. In addition to that, the system provides a mechanism for providing thermal control as well, so we'll get rid of all the thermal mass as well, and also, of course, provides a radiation shielding all integrated together. So this is is the basic concept. The basic concept is to develop an inflatable structure that's a laminate structure. And if you look here, the key elements are these little bags, little packets. We're using basically membrane technology, similar like desalination kind of technology, where they desalinate seawater using membranes. We're using those technologies then to process the air, remove carbon dioxide, remove trace contaminants, also to do water recycling in a laminate structure inside an inflatable habitat. So it sounds really way out there, and this is where I apologize for being so conservative. But the fact of the matter is we actually already have these technologies. We have them in our laboratory. We've been developing them for about the last 10 years. They don't exist as a laminate structure in an inflatable habitat, but they exist as racks, as pieces of equipment. You can take a tour over an Ames Research Center laboratories and you can see these elements there. The principal one is direct osmotic concentration. That's what got the whole thing started. That led to another technology called osmotic distillation, which then evolved into a lightweight contingency water recycling system. And what you see in those three technologies is a progression from standard life support type technologies, meaning a square metal box, which evolved then into a bunch of tubes that could sit under your seat, which then evolved into just a plastic bag that had no electricity, no power, no control, no nothing, a completely passive water recycling system that allowed you to recycle water indefinitely without using any electrical power whatsoever. Now those have evolved. Of course, there's some other technologies, mainly technology spin-offs that have occurred from that. And it turns out actually we can sort of produce power in some situations. And that's our forward osmosis power system, which uses the difference between salt water and fresh water to generate electricity. And then also a system that allows you to grow algae in the ocean as well. So I'm going to talk a little bit about the lightweight contingency system. That's the little bag that doesn't take any power, because it's the easiest one to understand, because it's a little bag that doesn't take any power. It's basically a little plastic bag. It has a membrane inside. And on one side of the membrane you pee, urine, or any other kind of wastewater. And on the other side of it you put Country Time lemonade, preferably powdered Country Time lemonade. And it turns out that the Country Time lemonade has a higher osmotic potential than the pee does. So the water flows across the membrane from the urine side, and it loops out the Country Time lemonade until you get it exactly the way you want it. And then you drink it. Sounds kind of gross, but it does work. Yes, we have that. Mary Roche's book, if you read her books, you get a chapter. Okay, so the technique that makes this work is called forward osmosis. And all of you sitting here think forward osmosis, what's forward osmosis? But you all know very intimately what forward osmosis is. It's basically what allows you to take water. When you drink the water, get it into your bloodstream. The small intestine of your body is a forward osmosis membrane. When you drink water, it goes into that intestine, and the osmotic potential of your blood is higher than the osmotic potential of what you drank. Therefore, the water goes across the membrane in your intestine and gets into your blood. If you drink seawater, the osmotic potential is too high, so it flows in the opposite direction. The water leaves your blood, it goes into your intestine, and you get very thirsty if you do that. It's also why the salt doesn't come out of the salt shaker on a humid day, right? Same thing. The osmotic potential is very high. It's how plants remove water through the roots, how they absorb water and the water gets into the roots. So it's a well-known technology. It's been around for a long time. What's really changed recently is the development of membranes that allow this process to work effectively. So in this basic concept, we're going to take this forward osmosis membrane and we're going to use it to recycle gray water in the wall of the element. The element is basically going to be that bag that I showed, just a much larger version of that bag. Your urine and humidity condensate will likely require some pre-processing due to the biological nature associated with them, and then be mixed with the gray water and then put in with these water bags. Now these bags then will be full of wastewater, and that wastewater will provide radiation protection as it's being processed into a purified product, and that product then will also provide radiation protection. In addition to that, we've done a lot of work looking at these membranes for basically sucking water out of the air, removing trace contaminants out of the gas stream. And we can use a specific type of membrane called a pervaporation membrane in a forward osmosis produced in these two applications. In the transit mission, that's a nitrogen-rich urine dominated brines that has a lot of calcium in it. And basically, the idea is that it would be combined with thermally stabilized solids and would be aerobically treated to drive off ammonia and odor-causing compounds and then dry into like a sheetrock kind of a material. Okay, I'm going to skip through these in a matter of time, and oftentimes I go into this, how actually the flow diagrams would go, but I don't want to run out of time here, so I'm going to run through that. The second part of this is air. How do we treat the air? And there's really two approaches to doing this. One's a pure physical chemical approach, and this is basically taking the membranes, having per-evaporation membranes that allow gas to transfer through, but they don't allow water to transfer through them, and then using that to strip out organics from the atmosphere, strip out carbon dioxide from the atmosphere. We can control the temperature of this water barrier to control basically the temperature inside the environment as well, providing some thermal control. And we can even use a technique by using salt water there to drive the osmotic potential high enough so that we can actually remove water vapor out of the air as well using these applications. The other approach is to use a biological approach, to use something like algae in these bags to make them clear and transparent and allow sunlight or some other source of light to be there to actually grow algae and then use the algae to convert the carbon dioxide into oxygen and strip it out, as well as using symbiotic environment where we're growing bacteria in with the algae to deal with the VOCs as that's kind of a biological scrubber. This is a picture of some work we've been doing using algae. That's a picture of a bag here, the gas exchange bag. Allows us to be able to grow algae inside these bags, stripping carbon dioxide out of the atmosphere, keeping them alive inside the bag. This is an example of those lightweight contingency bags we talked about. We can actually grow algae in those as well pretty effectively. This was a test looking actually at fouling. How many times can we grow algae, harvest the algae, and then reuse the bag over and over again. So in an algae system, which I think is kind of one of the more speculative systems, the basic concept is that the gas walls would be layered with FO water bags. These would be a 3-layer construction of clear polyethylene front and back and an internal polyethylene gas exchange membrane welded to the back. And that's basically the construction of the picture I showed you, the one that had the algae growing in it. And the idea is that this algae would grow inside these bags, would strip out carbon dioxide, would remove the volatile organics, and then every once in a while the person would have to harvest this algae, remove the biomass out of there, and then re-inoculate and start it again. And so potentially the algae biomass may have some value as well. So of course, this is kind of a crazy idea, right? I mean, it kind of requires you to build a big inflatable habitat and maybe launch it or put it out in the parking lot and make a demonstration project out of it, and that's really unlikely to happen. So our approach in the future has been to take a much smaller portion of it to develop it. And that is primarily around the use of the standard cargo transfer bags that are used on the International Space Station right now. So our plan is to modify those bag materials to make them into these forward osmosis type constructions, and then to bring them up onto the space station or into a chamber test facility and demonstrate that we can actually perform these functions, life support functions, just simply by taking the bags apart, unfolding them. So this is the original shape of one of these cargo transfer bags. And this is what it looks like if you kind of cut it open and spread it out. And then hanging these on the inside of a habitat, making them sort of into the walls of the inside of a habitat, and then demonstrate the capability to do water treatment and to do air purification using these types of configurations. And that's kind of a picture of what it would look like inside a habitat here. These are basically the bags right here. Right here. Okay, so in conclusion, I'd just like to state that this work was funded through a grant from the NASA IPP program, actually the Ames portion of the IPP program. The concept is based on existing technologies that we've been doing work with for years and years and years. Although the idea of putting together in this configuration is totally new, and there's of course a lot of risk and a lot of problems associated with it. I can't say that the whole thing is completely feasible, but I can say that the process by which we are screening these technologies and doing the demonstration certainly is feasible. We do know that NASA is probably going to use a radiation shield, and a water wall certainly is a primary candidate as a radiation shield. So there will be the opportunity to do this kind of integration in the future spacecraft. And that is the end.
sit over at the table. We've got 10 minutes to have a few questions, and then I'm sure our timekeeper will boot us out.
Oh, they're lining up. Oh, man. We're in trouble now. All right.
My name is Sherwin with Vector Engineering. I've been a vegetarian for over 20 years, and I'm getting dismayed that everyone seems to have meat in space. So I'm wondering, I eat a lot of hummus, not to this tonight. But is there a way to be a vegetarian in a long-term closed ecosystem?
Sure, absolutely. There's no question you can do it. You're proof that it's possible to be healthy and eat a vegetarian diet. It's just harder. And your health may not be as optimal as you may think. But it's definitely possible with your proof of it.
So I'm Ed Jones at Rocket Plumber Aerospace. And with a lot of plumbing experience, your idea of bags is innovative. But I'm looking at how do you get rid of the entropy? You're talking about forward osmosis into a salt solution. Then you have some dilute salt solution. How do you get the water back out of that salt solution?
So actually, in the flow diagrams that I skipped through, we talked about that. But we actually use a little RO pump to extract the water out of the salt solution.
And you also have all the issues, all the biological load that's going into the bags, going into the net. Actually, you have to deal with all the methane and CO2 gas coming off of it. That's a big separation issue.
Yeah, they do, but the technology that we're talking about, the direct osmotic concentration, the osmotic distillation, and the lightweight continuously, those are all common to those technologies. And those are all issues that we're dealing with right now in the operation of those technologies. And it's our feeling that there are relatively simple solutions to those problems.
So you still need lots of functions.
It ultimately won't be a completely passive system. That's for sure. There will be some hardware ultimately required, probably to put it together. But we're at the beginning of that process, and we don't really know entirely what those will be at this point.
Yes.
My question is, you gentlemen, man, was talking about the economic models for needle-type colonies. Does anybody have an economic model that works that doesn't require space-based solar power?
That's a good question, and I think the answer is no, or at least as far as I know. If you look at the original Ames study, they looked at that very carefully, and there's a paragraph in there where they say that no other substitute for space solar power is found that could support these very large colonies. On the other hand, doing something like producing oxygen from the lunar materials to make fuel was able to get the cost of the program down by about 1/3. So there are a lot of things that you can do to make money using lunar materials. And for instance, there have been studies on using that lunar oxygen to supply the satellites in orbit, and it's kind of marginal. But it seems like the key to the whole program is the combination of building the space solar power satellites at the same time as habitats and using extraterrestrial materials.
You guys have a lot of pieces of puzzle. And I was wondering, is there some organization or somebody looking at how they all will work together eventually, like the agriculture space, the water membranes, or some of that, how they affect each other?
That's supposed to be the brief of the Space Studies Institute.
I'm Mark Coffey, and I'm in the context of that building in the model. I think it's funny that you were talking about. My question is, I got the impression that you were sort of using the cost and the benefits, or just nothing I studied for your alternative model. And is that right?
So what we did, and Michael could chime in if he wants. What we did was we rebuilt the model from the information in the studies, And so we used the parametric for costs, and then we inflated the costs to, in that study, 2005 numbers. We inflated the energy costs, prices also to 2005, and that's what we ran most of those studies with. And then in that one curve, essentially we tried to make everything the same except for the size. And that was that curve that uses 1975 dollars in energy.
All right, well, it's really interesting question to point out. Estimates of costs, I don't know what makes sense to do.
Yeah, and that's, you know, for the study that we did, mainly we wanted to look at the size. You know, how does that size variable change? So for the resources that we had, which was essentially Michael and myself and you know, in the library, you know, we may just maintain the parametric values from your study, but obviously that's very conservative because a lot of those technologies have improved and become miniaturized, and so it begs the question of redoing the model, and you know, with new parametrics that are reflective of today's technology.
Hi. This on? My name is Gary Marks. My question is for you. Dealing with the waste decomposition, and I was wondering if there's anything with composting or using feces, because I know on BK you do get some gases such as methane. If there's any plans to study to utilize that naturally.
Yes, you can. If you so desire, you can produce a fair amount of methane. In fact, Professor Jewell is not here today because he's advising the government of Ontario about producing energy, methane, and so on from crop waste.
Thank you.
We have time for very quick questions.
It seems like a fair amount of thought and study has been promoted to sort of the normal byproducts of nominal human and animal interaction. Has any thought been given yet to what happens when you have disease?
Sure. If you have disease and there are microbial diseases, then those diseases can affect not just humans, but they can affect plants, animals, and the microbes. So these anaerobic digesters require a certain mix of species to operate correctly. So do the aerobic digesters, and you have to have the right mix of microbes in the other soil systems and so on. So the answer is yes, you can get sick digesters, you can get sick people. If you choose to utilize antibiotics in these systems, you've got to figure a way to get those decomposed so that they don't affect the other elements of the system. So yes, it's an excellent question. You can use antibiotics, but you have to make damn sure you get rid of them in the waste stream.
One quick note on that, in the biosphere, we never had any communicable diseases for the 2 years, except when the spare part was brought into an airlock and the person outside had a cold. And all of our microflora became identical between crew members.
I'm Silvano Colomban, NASA Ames. I came here in around 80 as just out of grad school to work on a cells system. We called that cells with the E after the C at that time.
Yeah, old terminology.
Right. So it's not that's been going on, but then it was taken over by Johnson, et cetera, et cetera. My question is, why does it seem that we're already starting over with that? It feels like fusion power. It's always 20 years away.
I think it's like many things. It's a victim of not having a consistent program that builds on previous successes. There's a need to reinvent and not invent it here. I can't explain that beyond the politics of the day. Maybe one quick question to finish off. We're good.
Yeah, I guess nuclear power looks like a pretty robust option. I sort of heard listening to some of the bio stuff that high power
very successful in the scientific and technical efficiency, using cobalt-60 to sterilize various things like potatoes and strawberries and so on to preserve them, and also shrimp. The relevant government body decided that even though it worked fine, it's somehow that gamma radiation might do something bad to the food stuff, and therefore it wasn't permissible to use. So the answer is sure that using that kind of system, which was intended to be a commercial system many years ago, and developed to financial feasibility, just didn't make it in the marketplace because it was stopped by federal regulations.
Yeah, you suggested that you were saying there's nothing else besides energy that can be practical to feed and to pay back